Good morning everyone. In the last lecture, we derived the dispersion relation for electromagnetic waves in plasma. So this is the corresponding equations where this epsilon omega, which is the function of omega and k, the frequency and wave vector into omega square is equal to c square k square. From that, we consider that when epsilon is a real quantity and it is greater than 0, we found that this k also will be a real quantity. Omega is real and k is real, and correspondingly a transverse electromagnetic wave will be propagated through the medium. Also, we consider that when epsilon is equal to 0, which will be corresponding to the propagation of longitudinal modes of waves through the plasma medium. Today we will be going into the detail about the transverse as well as the longitudinal modes of electromagnetic waves in plasma medium. So we started with the dispersion relations, and in the previous class we also considered that for a free electron gas inside the plasma medium, we found out that this epsilon omega, which is the dielectric functions, is related as is equal to epsilon infinity of 1 minus omega p cap square divided by omega square, where this epsilon infinity, which is the contribution from the ionic side. So we consider the influence of ion side. The electrons in this medium, in a plasmonic medium, plasma medium, which is an ionized gas. So inside the medium, the electrons will be moving and there are ions, positive charge ions. So correspondingly, we find out that the dielectric function is related as epsilon omega is equal to epsilon infinity into 1 minus omega p cap square divided by omega square, where omega p is the plasma frequency. So we consider that. So we can substitute this equation in this equation number 1, so that we will get the expression in this format, and we can consider different cases. For example, in these equations, so if you rearrange these equations, so if omega is less than omega p here, so if omega is less than omega p, this time the left hand side will be a negative quantity. Correspondingly, k square will be less than 0. So the k square is less than 0 means k is an imaginary quantity. So that means the wave vector is an imaginary quantity. So which corresponds to when k is imaginary in the medium, the corresponding solution of the wave equation solution will be of this form, which is exponential minus of modulus kx. So which corresponds to a damping oscillation. So that means there is no propagation of electromagnetic wave when the frequency is within this region, when omega is less than omega p, or when the frequency is between 0 and omega p, there is no propagation of electromagnetic waves through the medium. So that is one of the observations. So there is a characteristic frequency called plasma frequency omega p, below which there is no propagation of electromagnetic waves through the medium. So that is what we understood from these equations. Now we consider another case where omega, the frequency is greater than omega p. So we are considering the frequency which is the propagating frequency which is greater than omega p. So we can rearrange this equation so that you will get this format, because we cancel out this omega square here. Then you will get this format. If in these equations, so we can rearrange again. So you will get omega square will be equal to omega p square plus c square k square divided by epsilon infinity. So this will be a positive quantity, and so at this frequency range, the electromagnetic waves will be propagating. So this is corresponds to transverse electromagnetic wave propagation in the medium. The frequency omega corresponds to the transverse electromagnetic wave propagation in the medium, whereas from this equation it is obvious that omega is a positive quantity and k square k is also a real positive quantity, which corresponds to propagation of transverse electromagnetic wave through the medium. So the corresponding characteristics wavelength. So you got the omega p, the plasma. Omega p is the characteristics frequency above which there is a propagation of transverse electromagnetic waves through the medium. So we can plot a dispersion curve, the dispersion relation for this region in the plasma region, and on left hand side, on the y-axis we consider omega by omega p, and this is 1. So this omega by omega p 0, 1, 2, etc. like that, and this is also like that. So this is omega by omega p versus ck by omega p graph. So this is along x-axis, it is related to wave vector. So this is omega versus k relations. So that is the dispersion relation. So that is the dispersion relation. And here you can see that, so this straight line, so this is the straight line which corresponds to omega is equal to ck. So omega is equal to ck, which corresponds to this straight line. So on above this frequency range, so that means when omega is equal to omega p corresponds to this point, above this frequency range, the corresponding relation is omega is equal to square root of omega p square plus c square k square, which corresponds to the transverse electromagnetic wave. So this frequency corresponds to the transverse electromagnetic wave. Omega is equal to square root of omega p square plus c square k square. So this is the corresponds to the transverse electromagnetic wave, which can be propagated through the medium. So this below this point, so below omega p, so that corresponds to this point, that is a forbidden region. So forbidden region means there is no propagation of waves with frequency less than this region. So this region, the below bottom region, is called the forbidden region. So that is the forbidden region, and above this region is called the transverse electromagnetic wave propagation. So above this region there will be propagation of transverse electromagnetic waves through the medium. And if you want to know the corresponding characteristics wavelength corresponds to this omega p. So above omega p there is a propagation. That means the corresponding wavelength will be lambda is equal to 2 pi into c by frequency. So 2 pi c by omega p. So since omega greater than omega p equivalent to lambda less than lambda p, so there will be propagation of electromagnetic wave through the medium when the wavelength is less than lambda p of the medium. So when wavelength is less than this wavelength lambda p, the characteristics wavelength, there will be a propagation of transverse electromagnetic wave through the medium. So this corresponds to the the transparency of metals. So alkali metals, which is found to be transparent to the UV wavelength region. So UV ultraviolet in wavelength region, this medium is transparent. So transparency means the corresponding wavelength can propagate through the medium. So above the wavelength, above that characteristics wavelength, that is normally above UV region, the metals will reflect the corresponding wavelength. So reflection, due to the reflection, we will see colors, the reflecting different colors for the metals. So metals, most of the metals which are found to be transparent to the ultraviolet region, and so that this can propagate. So that corresponds to this lambda p, below lambda p, and above wavelength, these metals will reflect the corresponding wavelength. So that's why we see different colors. So if you want to know the corresponding wavelength for different metals, for sodium and potassium, you can see that the lambda is equal to 2090. So that is 209 nanometer, and for potassium it is 287 nanometer. So that is that is in the UV region. Now we will consider about the longitudinal plasma oscillations. The dilated function, which is a function of both omega and k. So for the longitudinal oscillations, corresponds to epsilon at frequency omega, which is close to or which is equal to omega L, which corresponds to the longitudinal mode frequency, which is equal to 0. The dilated function is equal to 0, which is the condition for longitudinal mode oscillations in plasma. So this will happen near K is equal to 0. And in a plasma media, as we discussed earlier, it is an ionized gas. So the plasma medium is an ionized gas where electrons is able to move freely. So inside the ionized gas there is a distribution of charges. The electron distribution will be negative charge distribution there. There is also positive charge distribution there, and there is a Coulomb attraction because of this charge distribution inside the plasma gas. So we can simply consider it as a box. Inside the box there are electrons which are freely movable with positive ion cores. So there is a charge because of the electrostatic attraction, the Coulombic attraction force. These electrons will be moving to one side, and there is a moving of positive charges to the other sides. So this will be keeps on acting inside the medium, and this will create an oscillation. So this will be creating a longitudinal oscillation. There will be a depolarizing field which will be generated inside the medium because of this charge distribution and movement of charge distribution inside the medium. There is a depolarizing field which will be arising, and this is the expression for the depolarizing field, which is equal to minus 4 pi p, where p is the polarizations. Now we know that in CGS unit, this is the electric displacement vector, which is D is equal to E plus 4 pi p. Since this is minus 4 pi p, the depolarizing field, so we substitute here, this will be equal to 0. So this will be happening for a longitudinal mode oscillations. The D will be equal to 0, and this is the expression for the dielectric function for a frequency omega, and at omega is equal to omega L, the expressions become 1 minus omega p square by omega L square. We replace the omega with omega L, and this will be equal to 0. This is the condition for longitudinal oscillations inside the medium, and from this expression, if this has to be 0, this omega L should be equal to omega p. So the longitudinal oscillation will happen at the frequency of omega p, that is the plasma frequency. So this is the representation of the electron oscillations inside the medium. So this is the longitudinal oscillations inside the medium. We can represent it using this figure, and we can consider this one as a metallic slab. So there is a metallic slab with this represents the cross section of the metallic slab, and where these positive charges representing the ionic cores. There is an electron displacement. So in this medium, for the longitudinal oscillations, the electrons will be displaced, and we consider the corresponding displacement as these negative charges. So this representing the electrons, and U is the displacement of electron gas inside the medium. So we represented U as the displacement, and corresponding field will be equal to, the electric field will be 4 pi p minus 4 pi p, which becomes 4 pi NE2. So this is the expression for the electric field due to the displacement of electron gas inside a metallic slab like this. Now we consider the equation of motion of electron gas inside the medium. For that, this is the expression for force using Newton's law, second law of motion, and this is the force due to the electrostatic field. And from this we can expand this one in this format, where U representing the displacement. So N M d square U by dt square representing the force this time, where N is the electron concentration, and that correspondingly this will be the expression for this terms, that is minus N E. So this is the force, this is also the force equations, and this can be this one can be formed in this format. This is equal to this, we substitute for E from this expression, equation number 1, so that we will get, this is the equation of motion of electron gas inside the medium, and we cancel this to N, and finally we can write the equation of motion in this format, d square U by dt square plus 4 pi ne square by m into u is equal to 0. So this is in this format, d square u by dt square plus some omega square u, omega p square u is equal to 0, where omega p is equal to square root of 4 pi ne square by m. So this equation is the equation of motion of a simple harmonic oscillator. So from this we can show this is the equation of motion of an electron gas undergoing longitudinal oscillations, where omega p represent the corresponding frequency of oscillations. So this equation represents the equation of motion of simple harmonic oscillator with oscillating frequency omega p. This is also the equation of motion of longitudinal electron gas. Thank you.